Hey guys, it's Casey and welcome back for another tutorial. Today we are going to expand on a little bit of kind of the math tutorial that I did before. I did a vector math video inside of like the three most important concepts that I believe you should master for blueprints, and I kind of want to expand upon that, not just with vector math, but just with some useful math that you'll learn along doing video games, and there's some very helpful tools that you have available to you. So the first one that I'm going to show you is we are going to go over the node called lerp. So what I'm going to do is I guess I should back up. This is the third person tutorial, just the default blueprint setup. I believe all I've done is I've set my lights to be movable, and I had to replace this cube because I was messing around for a minute, so that's the only things that I've changed. So I'm going to open up my third person character, and to do so all I did was click on it, and on the right side I did blueprints and open blueprint editor. And now what I'm going to do is I'm going to show you a node called lerp. So if we type in lerp, we'll get a few different ones. The one that I really want to go over is I'm going to go over a float lerp. So what a lerp really is if we highlight it, it says it linearly interpolates between A and B based on an alpha. An alpha is a value that goes from 0 to 1. That's what an alpha is. So halfway between A and B would be 0.5. All of A, if we highlight it, it says 100% of A when alpha is 0, 100% of B when alpha is 1, and if you're anywhere between 0 and 1, you'll get a mixture of A and B. So that can be pretty useful. One way that I've used this, I've used this a million times, but I guess an easy way maybe to visualize this is, let's say we had a variable stored inside of our character. Let's just say this was like our agility stat or something like this. We were using some type of like RPG with stats. I'm going to compile, and let's say like my agility was let's say 75. Then what we could do with this is we could convert this to a float, because I want to divide by this, and if our attribute is between 1 and 100, what I can do is I can then divide that by 100. Now you can see that if, say, my stat is 75, when I divide that by 100, it will turn into 0.75, and that's really useful because now it's normalized within a range of 0 to 1, so we can use it as an alpha. And then let's say on begin play, we wanted to set our character's movement speed. So I can grab my character movement component, I can set my max walk speed, and that is the walk speed of our character, and then what I can do is I can hook this up to our lerp. And I can say, based on my character's agility stat, or if we wanted to, we could rename that like our speed stat. Let's say when we have agility of 1, I wanted my move speed to, let's make our move speed like 100, and then with the agility stat of 100, I want our run speed to be 600. Now, what we could do is you can see that, let's see if I can kind of organize these windows side by side so we can see the math. So let's do that. So we can watch this value. Why can't we do that? There we go. And now what we can do is when we hit play, you can see that it set my movement speed to be 475. I believe you should be able to see that. We can make this a little bit bigger if we need to. And that, because we took our agility of 75, we divided it by 100, which gave us 0.75, and then when we lerped it between 100 and 600, our resulting value you see here is 475. Now you can see my character's running. And that if we kind of went back and we changed our agility all the way down to 1, and that we hit play, you can see I'm going to be insanely slow. And that just the same, if we set it all the way up to 100 and we hit play, you can see that we actually move decently quickly. So that's kind of what lerping can be useful for. And just remember, lerping is linear, if that makes sense. I believe when we highlight it, it says linearly interpolates. If you wanted it to be like more exponential, like you wanted these values not to be constant, because what basically is going to happen here is that the difference between 70 to 71 is going to be the same difference as 71 to 72, or the same difference from 1 to 2. It's linear, if that really makes sense. So this wouldn't be useful if you wanted it to maybe get exponential, that the higher it went, maybe there's some fall off, and early points in speed were more valuable than later points of speed. You wouldn't use lerping for that. But that's like one good example of how you can use lerping. Another very useful way that we can use lerping is we can kind of inverse lerp into a lerp. And I say inverse lerp because that used to be a node inside of Unreal. It looks like they took it out and they replaced inverse lerp with something called normalize to range. It does essentially the same thing. So if we got rid of our agility code and our max walk speed code, I'm actually going to do something a little interesting. So let's say with this cube over here, I'm going to put it at the beginning of the stairs, And that what I'm going to do is I'm going to say, based on how close we are as our character to this cube, I want to like raise and lower this cube inside of the world. So based on how far away we are, we're going to move this cube around. And that's what I basically want to achieve. And what we can do is we can use lerping and inverse lerping to achieve that. So what I'm going to do is I'm going to make this cube a blueprint. So I'm going to add a blueprint script to it. I'm not going to worry about renaming it. I'm just going to make it an actor. That's fine with me. I don't really need to do anything inside of that. And on begin play, I just need to get a reference to that cube real quick. So I'm just going to get all actors of class. And I just need a reference to the cube, so I'm going to type in cube, and you can see I have our cube blueprint. And then I just need to get out the first index of it, and I need to promote that to a variable. If you don't understand actor references, then I really recommend watching, I believe it was part 2 of my blueprint kind of essentials video. So I'm just going to name this variable cube. So now we have a reference to that cube at the beginning of the game. So what I'm going to do is on tick. What I want to do is I want to see how far away I am from that cube. And if you remember from the original vector math video, to get distance, what we do is we take the actor location of our targets. Oops, that's not right. Get actor location. There we go. We need the vector location of our target, and that we need also, if I copy paste this, we need the actor location of ourself. So now we have our 2 vectors. And now if we subtract them against each other, that gives us a line between the 2 of them, and that if we get the length of that line, that gives us distance. Wonderful. So if we want to test that out real quick, I'll do a little print string, and we will punch in that vector or that float, and we will test our distance. So once again, we're getting the location of the cube, we're getting the location of ourself, and then we're getting the distance between the 2 of them. So you can see it's 440. The farther I get away, you see the top left, the numbers get bigger. The closer I am, the numbers get super small. Perfect. So that works for me. But I know there's going to be a little bit of a weird thing going on here. Because we're also going to be moving the cube, I don't necessarily want to constantly be getting the actor location of the cube. I kind of want to store this as a variable. I want to store its original location as a variable, so I'm going to promote that location to a variable, and I'm just going to call this original cube location, so that we just get like where its starting location is, because that's really what the distance that we want to trace from, and I'm then going to punch that into our vector length. So I'm going to delete that print string. So with this length, what we can do is we can normalize it to a range. So what normalizing to a range does is if we highlight it, it says it normalizes a value to a given range. For example, if we take 20 and we normalize it to the range of 10 and 5, that would result in 0.25. If that makes sense, so we basically are saying what's our range. If we did like 10, as it says in the example, 10 to 50, if we went say 10 units closer to 50 because they're 40 away, so every 10 would be 0.25. When we're 10 closer to 50, that would be 0.25. And let's say we were 25 in the middle of range of 10 to 50. That would give us, is that 0.5? No, 20 would be 0.5. Sorry, that was a little bit of bad math there. But we'll see this in practice if that doesn't quite make sense. So I want the distance to be the value, and then the range we're going to normalize it to. Let's take a range minimum of 1, so that's going to be our minimum distance, and let's do our maximum distance to be like 1,000. And now what that will do is that will take our current distance, and it will try and normalize it, usually from a value of 0 to 1. I'll show you how that can kind of go outside of that, but we can even make this larger if we want to. We can make it even like 1,500, and that will try and make it from a value of 0 to 1 based on how far we are in the middle of 1 and 1,500, and we can take that and plug that into our alpha. And that what we can use is we can use this the lerp now, and we can make this a distance. So we can make it 1 to, let's do like 1,000. And this will work just like the lerp did before, and that what I want to do with this is I want to set the actor location of our cube. So we can set the actor location, and I just want to move it up and down in the air, so I'm going to break this, break vector. Why is that? Or no, we want make vector. Why am I doing break? Sorry, I'm doing it backwards. Make vector, and then I want that to be the z of the cube. Or actually, let's see here. What is the current z of the cube in the world right now? It is 250. So let's actually make that our minimum. Let's do that. So we'll make our minimum 250, and then we'll make the maximum 1,000. And that we will then take the original cube location, and we're going to break it. and that will be the x and the y. So we want the x and the y to stay static, and that we just want to raise it up and down in the air based on how far away we are from that initial location. So let's minimize this math and let's see that in practice. So you can see how far away I am to the original location of that cube. We can raise and lower it in the air. And if we pull up the math, let's see if we can get that inside of our window. Let's see if we can resize this so we can get that in there. Let's watch some values. So what we can do is we can watch our vector, our length, how far away we are. We can watch the normalization, and that we can watch our lerping. So let's do those three values. So you can see based on where I am, it says I am 1,052 units away from the original cube location. That results, when we normalize it, in a value of 0.701, in that we plug that 0.701 into our lerp, which then results in a value of 776z. You can see the closer I get, the smaller that vector length gets, the smaller that normalization gets, and that results in a smaller lerping value. So you can see how that works. And that if you see here, we can actually get our lerp to go beyond the 1,000. So if you see here, we are lerping between 250 and 1,000, but you can see we managed to get a value of 1,054. The reason being is that we plugged in an alpha that was greater than 1. So when you normalize to a range, what you have to remember is that if your value goes outside the range, like right here our distance is 1,600, we made our range max 1,500, so we went greater than it. It still tries to normalize it in a sense of it keeps its like linear standard to make it increment greater and greater, and that the alpha does the same thing. It kind of uses its marginal difference to linearly increase. If we wanted to, we could clamp this. So we could clamp this in several spots if we wanted to. If we wanted to, we could just do it like at the very end, and we could clamp our float. And what a clamp does is it just gives us a min and a max that we can plug in, and we can just plug in our min max to be 250, 1,000, so that now, if we get as far away as we possibly can, our value right here on the very end should never go above 1,000, and you can see there it freezes at 1,000 even though our lerp kicked out 1,196. So that's how we can use normalization with lerping, and I've done this a ton. This two sets of math. Usually I use inverse lerping in my previous games, but they got rid of that, and now the node is normalized to range. But I've used this method so many times for many different things. It's a really useful tool when you're looking to kind of manipulate data based on a certain value. You take that value, no matter how big, how small. Ours is in the thousands. We can normalize it to try and make it 0 to 1, and we can use that 0 to 1 to lerp. So that's very useful math. I really recommend learning it, or at least understanding it. It's a very powerful tool that you can have in your toolkit. So I'm going to take off all these watching values, and we will go on to our next piece of math. So let's stop watching that, and there we go. So what we'll go over next, let's see here. So I'm going to go back over subtracting vectors. I talked about this in the original vector video. When we subtract two vectors, this results in a line, and the magnitude of that line is the distance between the two actors. But this math also represents some additional things. Let's see, do we want to delete this? I believe we can just delete this. I don't think we need it anymore. Or at least I'll move this to the side. So we'll just move all this down. I'll just move my tick down, and we'll leave that data up there. And I'm just going to copy paste this subtraction. So this subtraction represents multiple things. And it really represents two main things for us. One, it represents the magnitude of this resulting vector when we subtract represents a distance, which we got here using the vector length. Sorry about that, I had a burp. And that what this also represents is it can give us a direction between the two actors, and that can also be very important. So if we can think about this, let's actually copy paste this down. What if we had the vector, let's say 1 1, let's pretend these are 2D vectors. Let's pretend this is like a 2D plane, like in old geometry grade school when you had just like the 2D cardinal axis. I forget what that's called. Let's say we subtracted 1 1 from 0 0. The result of this vector would be 1 1, right? We're subtracting 0 from it. It does nothing. But what does that mean? That means it's a line that's 1 1. So that means it can give us a distance between the two, but that also means if we added the results of this math back into this bottom value that we subtracted, that would result in an end location that is this top vector, if that makes sense. if we subtract 0, or if we subtract 0 from 1, 1, that gives us 1, 1. If we add 1, 1 back into 0, 0, what does that result in? 1, 1, right? And what if we flip these values? What if we had 0, 0, and we subtracted 1, 1 from 0, 0? That would be negative 1, negative 1, right? What if we add negative 1 back into 1, 1? What does that result in? 0, 0. So you can see how that also gives us a direction. Like, I hope you can maybe visualize that in your head, and we'll actually do some math here to actually show that. So, when we subtract two vectors, not only is it a magnitude that is the distance between the two, but if we add it back into this bottom vector, it will then result in the top vector, if that makes sense. So that can give us a direction. So let's use that. What we're going to do is on tick, we are going to draw a debug line. Let's draw a debug line. Our start location is going to be our bottom actor, so it's going to be our self. And that our end location, what we are going to do is we are going to normalize this vector so it makes it a distance of 1, and that we're then just going to multiply that by a float, and let's just do the distance of like 100, and that then, because this is relative, we have to add that back into our own actor location, and that is our end. So I'll go over that math real quick. I'm just going to change the line color. Let's make it like red, pink, whatever. Duration, let's do like 0.1 point tick. We need it to be tick. Can we just do like delta world seconds or something like that? I think that might work. Thickness of like 5. So what we did here, this represents, we're worried about the direction that this vector represents, so we're going to normalize it. If you remember in the first video, that makes it a length of 1, and that since that vector is a length of 1, when we multiply it, we can make it equal the magnitude of that line, the distance of that line is equal to that float that we multiply it by, and since this is relative, we just need to add that back into our bottom actor. So what this should represent is that this should always give us a line of 100 units pointing in the direction of our cube. So let's try it out. Let's see here. I don't think that delta world seconds worked right, so let's try the duration. Let's try the duration to be like 0.1. Let's do that. Let's see. Did I do my math right? There we go. So you can see how this line is always going to be pointing towards our cube. So you can see how this could be useful in that with this vector math, in the previous example, we were using it to get the distance between us and the cube. We can also use that very same subtraction, and that we can use it because it also represents a direction. And if we normalize it, we can then multiply it by a float to extend it 100 units out. So now what we're doing is we're using that subtraction to give us a facing between two vectors. This can be insanely useful. Say you had a spell that say this was like an RPG. Say I was kind of not exactly facing our cube and I wanted to cast like a fireball. Well, if I need to give a direction to that fireball, I need to give a vector to that fireball for it to throw at our target, I need to know what the vector facing between my actor and our target is. This gives us perfectly, as you can see the line here, I could feed basically this line to our fireball, and I could say throw the fireball along that vector to hit that cube. So that's what we can also use subtraction for, is that we can use it to give us direction. So I hope that made sense there. So I think we have, let's do 2 more things. I think I have 2 more things that we can use, and they're also somewhat related to this. Another very useful thing that we can use that is somewhat along these lines but slightly different is that we have a node called find look at rotation. And what we can do is we can feed 2 vectors into it. So let's copy paste this data here. And what we're going to do is our start is going to be our current actor, so our third person character, and our target is going to be the cube. And what we're going to do is I'm going to break this, and what I really worry about is I worry about the Z. The Z is the, I'm not sure how to explain it. Our Z, without visualizing it, this is our Z right here. Our Z is just our ground-based rotation. So, like, are we facing the cube is basically what we're looking at there. And that's all I really care about. And we're going to print this Z. So what we're going to do is we are going to get back a print string, and we're going to throw that into our string, and that we are going to get rid of our draw debug, and we're going to move this back to the side. So now what we're doing is we're using this node called find look at rotation, and what we do is we plug 2 vectors into it, a start and a target, and what it will kick out is it will kick out a rotation that if our start actor faced, he would perfectly face the target. And what we're going to do is we're going to print this to our string. So if you can see here, when I'm about right here, we are almost at perfectly 0. So if we looked at the rotation of our character, you could see our z is going to be very close. Actually, that's weird. It's not close to 0. I'm not sure why that is, actually. Huh, that's actually interesting. Let's ignore what I just talked about right there because I'm not really sure why that is. However, if we look here, you can see as I run around this cube, you can see we get closer and closer to 180 until I get to right here, it's 180, and you'll see it flips to negative 180, and if I go all the way back around, it's 0. What this is doing is it's kicking out a rotation, and we're just looking at the z here, that if we use that rotation, it would perfectly face us at that cube. So what we can do is we can actually use that to lock the rotation of our character. So if we did set actor rotation, we can set the actor rotation of ourself. And once again, we're just going to be worried about the z here. We don't want to manipulate our pitch or our roll. So I'm just going to make rotator, and we're just going to plug that z into the z there. So we're just using that value that we just printed to constantly set the rotation of our actor. So now that we can visualize it, you can see no matter where I move, we will always be perfectly facing, at least our yaw is perfectly facing that cube. So that's what we can use the find look at rotation for. And it's very similar in a way to the math that we did before to find direction. This is direction in kind of like vector space if we were to think about rotation as a vector, in that this is if we were looking at rotation as a form of a rotator. So basically that's what you can use there. They're very similar, and you can use them kind of interchangeably in a way if you know how to convert between rotators and vectors and stuff like that. But yeah, that's what we can use find look at rotation for, and I've used this a lot. I use this a lot for things like AI. It's very useful to get your AI to face what you need it to face. A node like this is very useful for that. If we need our AI to face a certain way, this is a very, very useful tool. And there's one more way that we can kind of look at rotation, and that is dot product. Dot product and cross product are these very super efficient ways of dealing with math. And I'm not experts at them, so I don't want to go over it too much, but I do want to go over dot products. So dot products is a way of getting back whether or not a actor is facing something, I guess is a way to look at it. If we just type in dot product, you can see it wants two vectors, and like our find look at rotation, we could use that in a similar way. However, there's also a very useful dot product to where if we type in dot product again, you can see we get dot product 2, or what I usually use is we can get horizontal dot product 2. And what basically this is going to do is this, I believe, it's going to ignore the pitch in the roll, I believe. And I believe this only looks at our yaw. I think it only looks at our yaw. Ignoring Z. I think that's what it cares about. So what we're going to do is we're going to feed it two actors, and this will work exactly the same here if we plugged in our actor locations. But here it's very useful in that we can just plug in actors. So what we can do is I can plug in our cube as our other actor, and our target is ourself. So you can think about it as we're starting at ourself, and we're looking at the cube, and what we're going to do is we're going to get the dot product to that actor. So what we're going to do is we're going to print this. I'm going to show you what this represents. So I need to plug that into the string. So now we're going to look at what does this really represent. So this is going to be kind of interesting here, in that if we look at our cube perfectly, you can see it's a value of 1, or it's at least a value very, very, very close to 1. There we go. If I perfectly look at the cube, you can see it's a value of 1. And if I start turning my third-person character away from the cube, you can see the value gets smaller and smaller. If I look perfectly perpendicular to the side of this cube, or is that perpendicular? I guess you could maybe think of that as perpendicular. You can see the value turns into 1. Like if I was perfectly like a 90-degree angle looking away from the cube, it should be a value of 0. And if I look all the way kind of 180 degrees away from the cube, or perfectly away from the cube, you can see it's negative 1. So what we can do is dot products are a very efficient mathematical tool to kind of find what something is looking at. And I use this for AI. Say I know my AI is near its target. Like, let's say I have a zombie, and I want my zombie to attack whatever it is, a barricade, a player. I can find out by using vector math to see how close my zombie is to maybe the player. But then let's say I don't want my zombie to be able to attack the player if he's looking away from the player. So I can use the dot product and say, hey, how close to a value is your dot product of 1 zombie when you're looking at the player? If you're something like -1, you're looking away from the player. I don't want you to be able to attack the player. But let's say if your value is something greater than like 0.8 or 0.7, which means like the zombie might be facing like this to the player, I think that's good enough and I'll let you attack the player. So the closer to 1 your dot product is, the more you're facing your target. If you're in the negatives, that means you're facing away, and if you're at 0, that means, at least how I view it, as like perpendicular. So these tools can be really, really useful. Sometimes for like AI, sometimes for just finding facings. All of these tools have their places, and I have used all of them. So I hope they were useful. Let's see if we can go back over them. The first thing we did is we did lerping. Lerping is if we plug in alpha from 0 to 1, we can move between two values, and we can also lerp with vectors. That can also be useful in that we can get a distance between two vectors based on an alpha of 0 to 1. That's also really useful. You can lerp a lot of things. If we type in lerp again, let's see. We can lerp colors, we can lerp rotators, transforms, vectors, floats. You can lerp a lot of things. Also, the next thing we did is we used normalize to range to take some arbitrary value and then move it into a space of 0 to 1 so that we can use that as our alpha to lerp. That's also really useful. After that, we subtracted two vectors to get a, where was it? I think it was right here. We subtracted two vectors to give us kind of a direction, and that we can use that direction to do things like cast spells or maybe shoot bullets or something like that. Another way that we can kind of visualize this direction is that we can use the node find look at rotation, and that we can plug in two vectors to get a rotator output. Also pretty useful. And then the last thing we used is we used dot product, and what this is, it gives us, if we highlight it, it gives us a value. It should give us a value from -1 to 1. However, it result as it says in -2 if this just fails to run, and that is useful to know whether or not our one target is looking at another, or we can also do the same things with vectors if we did, or as we have right here. You can do dot products with two vectors. This can be very useful for things like AI, or to know if a player is looking at something. Say in a horror game, you wanted to know if the player was looking down maybe a hallway so that you could spawn a jump scare. This would be useful, because if your player is not looking at where maybe that jump scare is coming from, you probably don't want to make it happen. So that could also be a reason to use dot product. Dot product, the reason why you really use it over maybe other forms of math is that dot product and cross products are very, very efficient math tools. It's a lot of math there's several ways of doing things. There's several ways of kind of achieving the same outcome with like vector math or math in general, but a lot of the keys are, what is the fewest amount of like calculations that I have to do to get that result? Dot products are one of those things that is super, super efficient. So I hope that was useful. I hope you maybe learned some new tools that you can use while making your game. If you have any questions, please let me know, and I'll see you guys in the next tutorial.